car here? Nope, no car. How about, yep, no marks here. Smith? We have a Smith. Go once. Twice. Not yet, anyway. Davis is online. So you're here. Mark is online. Newton? No Newton. All right. Cunningham is online. Faulkner? That's all you. Stanley? Here yet? Whitaker? You? Strickland? Good. Vega? Fisher is online. Page? Valdez? Sims? Oh, what's Sims? Online? Not online. Zell's online. The Gene's here. Black. 8 o'clock. Slowly start. Some people show up, either online or in person. First of all, let me explain what's going on with the exam. So I got up Friday to administer the exam. Obviously, I'm checking emails as I'm waiting on you guys to turn the exams in. I have to say overall, I'm about to preach to the choir. If you're listening to me, this probably doesn't even pertain to you. But how many times did I say that the exam was going to be on Friday? Verbally and in writing, the exam was going to be on Friday. I said it over and over, and then I got some emails. I didn't know the exam was on Friday. And how many times did I say, hey, there's study guides. You guys should do the study guides. I'm going to use the study guides to write the exams. You can get extra credit for doing study guides. And then I got emails the night before. Hey, you're going to provide a study guide for the exam? So, and then other ones, this one's not as bad, but people turned it in after 9 o'clock. But I told you lose 10 points for every minute you turned it in late. So anything obviously after 9, it's a 0. So it stopped taking exceptions after 9. So I got emails for that saying, hey, I didn't know it was going to close after 9. But even the instructions said that. I said this over and over, verbally and in writing. You guys do these things. Not you guys. Again, I'm preaching to the choir, I think, because you're paying attention. A lot of people aren't. So anyway, just to be honest, it was just really upsetting. So I just didn't even finish grading the exams. I just took a step back. I'm like, all right, I'm going to do this later this weekend. And I'd intended to do it later this weekend, that weekend. And I traveled. I had to go to Ohio for something. And I got sick, so I've been in bed sick all weekend. So I still have to finish grading the exams and checking emails. So if you think I've been ghosting you, I haven't been.
Thought you would ghost.
Yeah, I was kind of ghosting everybody. I thought I was kind of ghosting everybody. I just needed to break in. Like I said, I was really, really sick. So I'm going to get to the bottom of the exams today. I'm going to finish grading them. You guys will all have your grades. Also, here's this one I don't expect people to get. So I'm not upset about this one. But if you watch those videos of the exam reviews, the second one.
I sent you an email about that.
Okay, well, one of them said, hey, it's going to be a really, really weird question for extra credit. You guys remember the really weird one that made no sense? Well, the answer to that one was tissue. And the video just told you the answer is tissue. And anybody who got that right will get a 10% boost on the grade. Of course, if you didn't get that, that's not the same as not paying attention. That was some really hidden stuff. So anyway, I'm going to finish the exams up today. A lot of people have zeros because they didn't know the exam was on Friday or because they turned it in after 9. But it is the first exam, so I'll probably let them retake it. However, that's not fair to you guys. So probably, and I don't know yet, so probably what's going to happen is that everybody's going to be allowed to retake the exam, and you're going to get an average of the 2 grades. So for example, if she got an 80 the first time and then she gets 100 on the retake, then she'll end up with a 90. Those people who have a 0 right now, if they get 100 on the exam, they're going to end up with a 50. But it's better than 0. So if we do that, the retake will be open book and it won't be timed. So you just go do it. Take your time and just look it up and find all the answers if you need to. Sound good? All right. So again, if you sent me emails about exam grades and all that, like I said, I'll get to it. If you feel like you didn't do good, you'll be okay because you're probably going to get a retake, even if you got 0. But like I said, Best case scenario, you end up with a 50, but a 50 is still better than nothing. And we're in college. You guys are in college now. I don't feel like I'm being too strict here. Like I told you when the exam was going to be and when it was going to close and all that. And you get the second chance. Anyway, now that we're done with all the bad news, are there any questions, I guess, other than exam stuff? Because, like I said, I'm going to get to that. Any other questions about things in general? No? All right. You'll notice we are going to chapter 5. We are skipping chapter 4. Wouldn't hurt you to read chapter 4 in the textbook. You definitely don't need to memorize it. Chapter 4 is all about the different parts of the cell and how a cell works. So what we're about to learn in chapters 5, chapter 6, chapter 7, chapter 5, chapter 6, chapter 7, chapter 8, chapter 10, all these chapters that are coming up is going to be specific things about how cells work. So because of that, I'm skipping chapter 4. You're not going to learn all the different organelles in chapter 4 because in these next coming chapters, you're going to learn all these things. So that's why we're doing it that way. So anyway, that being said, let's jump into chapter 5, how the cell works. And I will say this before we get started. You could essentially call this next exam, talking about the properties of life, this next exam is all about processing of energy. If I had to sum it down into that one thing, that's what this whole next exam is about. These next 3 chapters are all about the fact that life, remember like we said in chapter 1, you have to process energy. You have to change it from one form to the other. Anyway, your book always starts off with these little pictures. I like to call it the guessing game. Why not? Might as well look at it. Any idea what this might have to do with a cell? Like how cells work? If you don't guess it, I don't blame you because it's really off the wall. Or here's a better question. Why would somebody be wearing a suit like that? Even that's kind of stretching it. Not get sick, that would be good, yeah. And that, especially these days, right? In the time of COVID, I would think more of that. Your book's getting at nerve gas. So apparently this guy's dressed up to prevent nerve gas contamination. And what you're going to learn in this chapter, I'm not going to specifically teach you how nerve gas kills you, but by the end of the chapter, when you understand how the cells work, you will actually understand how nerve gas kills you. So that's fun stuff, right? What's the other one? Oh yeah, the pizza. Let me look. I have little notes to remind me. Oh yeah, the pizza and these people walking. What do you think those two have to do with each other? Good, exactly. Specifically, the type of energy in this picture would be, well, if you want to guess, what kind of energy might you get from this and might you use right there? You get the energy, a certain type of energy from this, and then you use it there. Calories, right? You guys all know what calories are, but you can learn a little bit more about it in this chapter. You're going to know exactly what a calorie is. And then the beef jerky and the raisins. What in the world might those two things have in common and also have anything to do with cells? Any guesses? How do you make those two things? Yeah, that's right. You dry them up. So you're going to learn about a process called osmosis. And then you're going to be required to make me some beef jerky. No, not really. Would be a lot cooler if you did that. Anyway, as always, the beginning chapter starts with this, biology and society, and he talks a little bit about how that chapter is relevant to everyday life, but I'm going to skip it as always because you will not be tested on it. But as always, I do recommend that you read it and let me know if you have any questions. All right, so this chapter is a big one. It's broken down into 4 main bullet points. First of all, we're going to talk about some basic energy concepts. Hopefully a lot of this is review for you. It's not even specific to biology, it's just a physics discussion, basically. Then after that, we're going to talk about ATP and cellular work, and that's a really, really important one. Then we're going to talk about enzymes, which we've already hinted at when we talked about proteins in the last chapter. And then finally, we'll talk about membrane functions. And under some basic energy concepts, the first thing we're going to talk about is the conservation of energy, and you guys probably already know this. First of all, does anybody know what energy is? I mean, we all do, but now that you're sitting here in a biology class, how do you describe it? What is the definition or description, whatever? Any guesses?
The book says the capacity to cause change.
Correct. And you do need to know that for the exam. Energy is the capacity to cause change. Some forms are used to perform work, such as moving an object against an opposing force. Obviously, you don't need to memorize that one example, but yeah, that person, there's energy being used there, right? He's exerting energy. Well, either pushing that thing up the hill or just keeping it from rolling down, whichever it may be. But yes, you need to know that energy is the capacity to cause change. So again, in this example, if he's pushing that thing up the hill, the energy is being used to change the position of that rock. If I go to the thermostat, turn it down, right, we are expending energy, electrical energy, to change the temperature in this room. It's the capacity to cause change. Any questions about what energy is? All right, here's one that you guys, I'm sure, know. So don't feel shy. This isn't a trick question. Probably thinking this is too easy. But it's not. Does anybody know the two basic types of energy? Surely you guys do. You just don't want to say it. All right, let me give you a hint. Here's the first one. The first one, before I tell you, the first one has to do with movement. The first kind of energy is movement. Good. Kinetic energy is the first one. That is energy in motion, and you need to know that. Kinetic energy is the energy of motion. So again, if I'm changing the temperature in this room, I'm changing the molecular level, the speed at which the air molecules are moving. That's kinetic energy. So now that we know the kinetic energy, what's the other one? Good. Potential energy. And that's stored energy. So it's basically kinetic energy is the energy of movement. Potential energy is stored energy. And some of that is very common sense. So I think when most people think of potential energy, they think of this little concept right here, where you would say, which one of these erasers has more potential energy, A or B? B, right? Just because it's higher, right? It has more potential energy due to its location. I think that's the one we're all really familiar with. But in this class, that's actually the one that's a little bit less important. This class, what's more important is potential energy due to structure. And I think the best way to put this for you guys to remember it and to know it, it's a little bit of an oversimplification, but it'll work for this course. However much energy it takes to build a structure, that includes the cellular structures too. However much energy it took to build that, that's how much energy is there to be released when you disassemble it. So remember last chapter and the chapter before that, we talked about building molecules, all those dehydration reactions. Those all took energy, right? It took energy to build those molecules. Some of which took more energy than others. And again, however much energy it took to build it, that's how much energy there is to be released. Sort of like, now I'm going to come back to this concept. If you've ever shot bow and arrows, the harder they are, generally speaking, the harder they are to pull back, right? That's more energy to put into it. That's how much more energy is going to be there to be released. Or there, it gets released when you release the string. So anyway, are there any questions about the difference between kinetic and potential energy? All right, you need to know those for the exam. But again, for potential energy, we're more concerned about the potential energy of structure. That does include molecular structure and cellular structure. So when you think of structure, you don't have to think of a building. Literally think of a molecule. That's the same kind of structure we're talking about. Then there's another concept that you need to know that you probably already do know, but the conservation of energy. Energy can't be created or destroyed. It can only be converted from one form to another. So when I clap my hand, I was literally converting the potential energy stored in the structure of the molecules in my cells. I used that to move my hand. That was kinetic energy. Then they hit it. Then that caused some kinetic energy of the air, which you took as sound. So in that case, it was sound energy, right? Didn't just get destroyed. The energy just converted to the kinetic energy of the air, and you heard it. And of course, some of it was absorbed by my hand, and some of it was lost its heat, but we'll talk about all that later. And of course, this bullet point right here is the main purpose of this whole next 3 chapters. Like we said, chapter 1, when we looked at the properties of life, life depends on the conversion of energy from one form to another. So that's why, as boring as this might be for some of you, these next 3 chapters, it is very important to understand how life works. You have to understand how we change energy from one form to another. Any questions about this slide? Oh yeah, I guess if you're online, you're going to need some attendance words. So the first word for attendance, let's say fire is the first word for attendance. like something you might cook over, or a bonfire, something like that. All right, so there's no questions on this slide. The next slide I'm going to show you is just a picture kind of demonstrating this idea of the conservation of energy, where it can't be created or destroyed, just converted from one form to another. So here we go. Might as well start at the top. This person, at least in this system, has the greatest potential energy, right? At least while they're doing that. And they jump, and when they jump, they convert that potential energy into kinetic energy because they're moving down. When they hit the water, again, you hear it when they hit the water, so that's kinetic energy. So all that energy is being, I don't want to say lost, but it's no longer kinetic energy. And then they just have the least amount of potential energy. They go back up, the cycle continues, you guys get the picture. Any questions about that slide? It's not very important, it's just a visualization of that relationship between potential energy and kinetic energy. All right, the next slide, we're just going to go right past. If you download the PowerPoint, you can watch it. It's a little bit of a animation that talks about some energy concepts. All right, next thing we're talking about is heat. And I've kind of hinted at this before. This is not the first time we've had this discussion, but it's the first time we're officially having this discussion with the writing on the wall, so to speak. First of all, what kind of energy is heat? If you had to break it down again between potential or kinetic, what type of energy is heat energy? Does anybody know? Well, there you go. That's right there. It's kinetic energy. You need to know that. Because it is really the random motion of matter. So again, if I were to say I'm going to turn the heat up in this room, that means I'm going to make the air molecules move faster. Or if I'm going to make it cooler, I'm going to make the air molecules slow down. If I rub my hands together, they're going to get hot eventually, right? They're going to warm up because that is the motion of matter. I would say, okay, sorry, this next, heat is the most chaotic and disordered form of energy, but I think the most important things you need to know about heat are that it is kinetic energy and that all energy conversions generate some heat. So if you ever get a question on the exam or a study guide, it makes no sense, but then it says something like, somebody was doing this, it was kinetic energy, and then they did this, but what happened to the energy? Where did it go? The answer is, some of the energy must have been lost as heat. Every time you go from one form to another, you'll lose some heat. The next concept, I'm just going to put a big old X through this. You'll have some questions on it for the study guide, but I'm not going to put it on the exam. Entropy is very important when you're looking at this thing mathematically. Like there's mathematical equations for all this stuff. Like when when chemistry is done and you're not looking at, this many molecules plus this many molecules gives you this many molecules. Sometimes you also need to look at how much energy is lost, how much energy is needed, blah, 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 blah. But since we don't do that, we don't need to worry about entropy. Mathematically, entropy is very important, but for our purposes, if that was never in the book, you could do just fine for the rest of the semester. So, again, for the exam, I'm not going to ask you anything about entropy, but just so you know, entropy is the measure of disorder or randomness in a system, and every time energy is converted from one form to another, entropy increases. So, for the study guide, because the question is on there, you should just associate entropy with randomness. So, this thing is highly ordered, right? Just a bunch of little things put together in a sphere, and then when they kind of diffuse and they're less ordered, then that is an increase in entropy. Again, not a very important concept for us. Any questions about this slide? All right, make sure you know about heat. That's an important concept. Next thing, this is also a very, very important concept. Actually, really, really important because this is almost all we're going to talk about moving forward. It's chemical energy. Chemical energy is pretty much what we're going to talk about for the most part, at least for the next 3 chapters. So molecules have a form of potential energy called chemical energy. That's what I was saying earlier. When I first mentioned that potential energy is stored energy due to location or structure, and I said structure is the thing that we're going to focus on the most, right? And I said however much energy it takes to build something is how much energy is going to be there to be released. That's what I'm talking about. So when I'm saying the structure of something, like I said, when you build a molecule, that's chemical energy, right? It's the chemistry that built those molecules. So it's chemical energy that we're talking about. And again, that energy is due to the arrangement of atoms. So again, it takes energy to build molecules. Then if you break those bonds, you break those molecules down, then you will also release that energy. All right, so what are these two people doing? They have a magnet. He has a magnet. They, whatever. Both of them have the north end pointing towards each other. So do you think they're having a hard time pushing them together, or do you think they're having a hard time keeping them apart? What do you think's happening there? Hard time pushing them together, right? Because the likes repel. That's a good concept, right? You guys probably already familiar with that, right? The like parts repel. Well, remember, let's back up to chapter 2. What is on the outside of an atom? Of course, the exams, you guys maybe a brain update because the exams are. What's on the outside of an atom? The inside is the nucleus. What's around the outside of an atom?
The valence shells.
Good. Specifically, which are the three parts of a?
Oh, electron.
Yeah.
Sorry.
Maybe I was too broad for the question. Yeah, electrons are on the outside of an atom. First of all, before I say this, let me say this too. I'm about to really oversimplify this. I've got to tell you, it's not 100% the best description. It's the best way to describe it for this course, and the best way for you to understand the concept and remember it. But anyway, so we know that the electrons on the outside of the atom, right? And what charge do electrons have? Good, negative. So if you have two atoms and you're trying to push them together, and they all have a cloud of negative things on the outside, they're going to be like this, right? They're going to repel each other. That's what's going to happen. So it's going to take some energy to push those things together, just like those two people are putting a lot of energy into pushing those things together. Same thing with molecules and atoms. Right? It's going to take energy to put those things together to make a molecule. So that's what we're getting at with this chemical energy. So again, however much energy it took to squeeze those things together until finally they clicked and they stayed, that's how much energy will be released once you break those bonds. Does that make sense? All right, and again, that's the concept I was saying earlier. I don't know if you've ever shot a crossbow, but however much energy was used to pull that string back, that's now potential energy. That's almost like chemical energy. Once you pull the trigger, you release it, and that's turned back into kinetic energy. That's the same thing with chemical bonds, right? However much energy was used to pull the string back, i.e. make the bonds, that's how much energy is there to be released once you break those bonds. So any questions about this slide? Okay, again, this is the most important concept as far as what we are learning for the next 3 chapters. It's all about chemical energy in different forms or another. Your book points out the cells and engines, like gasoline engines, car engines, motorcycle engines. They use the same basic process to make the chemical energy stored in fuels available for work. So for us, the fuel is the food we eat. For our engines, well, depending on what kind of vehicle you have, it's the gasoline, right? And you've already seen this picture. This is from chapter 3. Chapter 3, we're talking about the similarities of structures and functions. That's octane. Hopefully you recognize that as a triglyceride, and you can say, oh yeah, those fats, right? Those fatty acids look a lot like octane because they have similar structures and similar functions. And as we know, basically this is what the slide is saying. So we put in all these big fuel molecules, and then our body just breaks them down, and that releases energy. Or the car breaks down those molecules, and that releases energy. And that's what this next slide is, just a visualization of what this slide says. So again, you put in the fuel. In the case of the vehicle, it's octane. In the case of us, it's food. We're going to talk mostly about glucose. Almost every conversation we're going to have for the next 3 chapters is going to be talking about glucose, but obviously we eat other stuff. We'll cover that later. And again, we break it down in the presence of oxygen. We release energy, heat energy included. And then the byproducts are also the same, carbon dioxide and water. But we'll also talk about that later too. Point here is, again, we take big molecules, we break them down in the presence of oxygen into smaller molecules, and when we do that, we release energy. And I'm skipping some things like ATP and all that because we're going to talk about it later. So any questions about this? All right, here's another important concept where we're going to have a whole chapter for it. So this is just your first introduction. Cellular respiration. You do not need to write down this definition. Like I said, there's going to be a whole chapter where we talk about cellular respiration, and you're going to need to know it basically inside and out. So I'm not going to ask you the definition of it, but the definition is the energy releasing chemical breakdown of fuel molecules. Just like the pictures I showed you earlier, right? You put in the fuel, the big fuel molecules, you break them down into smaller molecules, that releases energy, and that energy is used. And that is what cellular respiration is. So it's not just breaking those fuel molecules down and releasing energy. I think it would be a lot more efficient if we could do that, but our cells cannot do that. That's the thing you might not know. So when we eat those fuel molecules and break them down and they release energy, our cells don't directly use that. First, they've got to store that energy in a form that the cells can use, because they cannot use that directly. And we're going to talk about this bullet point a lot. There's even a molecule that we're going to talk about. But yeah, that's a very, very important bullet point. Not to study and memorize it. I'm just saying that's very important. Like, we're going to talk a lot about it. Here's a number you need to know, and hopefully by now you know I'm not big into numbers, but this is one you need to know. About 34% of your food energy is converted to useful work. So of all the food you eat, only about 34% of that energy is actually put to use. The rest of it is released as body heat, which is why I have this picture of this infrared looking at this person. You can see the heat that person's giving off. And that's where your heat comes from. So yeah, there's the one slide where we talk about cellular respiration, which is funny because, again, we have a whole chapter coming up about cellular respiration. And I will admit, it is a tough one. I try not to make it tough, but it is what it is. I guess the second word for attendance would be this one right here, heat. Anyway, any questions about this slide? All right, this next slide is probably one of the more practical slides, the thing we're about to talk about, food calories. That's very practical for you guys, right? Your everyday life, you deal with food calories. You don't really think about this other stuff in your everyday life. But on the flip side, even though there might be a couple questions about calories on the exam, like one or two, in the grand scheme of this semester, it's not a very important concept. But let's talk about it anyway. What is a calorie? You do need to know that. A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So I love the metric system. Their stuff makes sense. It's all based on water. But yeah, you need to know that. 1 gram of water by 1 degree Celsius. So 100 calories could raise 100 grams of water by 1 degree Celsius. Or 100 calories could raise 1 gram of water by 100 degrees Celsius. You can see how that works, right? So that's what a calorie is. You need to know that. Here's where it gets a little bit confusing, though. Most of you, I would assume, probably when you think of calories, that's probably not what you're thinking of. What you're probably thinking of is this: food calories, or calories with a big C. Those are called kilocalories. So if your soda says 120 calories, that doesn't mean this. Doesn't mean there's 120 calories. That means there's actually 120 kilocalories. So 120,000 calories per serving if your soda says 120. That one's diet out there. Otherwise, I'll look at it and show you guys. Now in the UK, do the food labels say kilocalories? No, they just say calories with a big C.
I think it might be like certain foods do certain things.
Okay.
Kind of, but it's more likely just.
Okay. When I was in Australia, it was kilocalories. That was the first time I'd seen that. I was not a biologist back then, so I was like, what the hell is a kilocalorie? Now I know. But anyway, yeah, know that. Know what a calorie is with a small c. Know what a calorie is with a big C. There's some really confusing, not really confusing, slightly confusing questions about this on the study guide. But don't let it overwhelm. If there's any questions about it, there's only going to be one question about it on the exam where you have to do some math. Admittedly, it is a little bit hard. But again, it's just one question. So if you feel like you can't get it, don't worry about it. Because it's not that important for the grand scheme of the semester, and it's not going to be that important for your grade because it's only one question. Anyway, let's move forward and talk a little bit more about calories. Now, this next slide is going to look overwhelming, and there's nothing to memorize here. It's just an example. Like I just said right here, if a calorie can raise the temperature of 1 gram of water by 1 degree Celsius, I said 100 calories could raise 100 grams of water by 1 degree Celsius, or it could raise 1 gram of water by 100 degrees Celsius. That's kind of what I was getting at, and that's what this next slide shows you. So if we're talking about calories with a big C, which is kilocalories, there's just so many different ways of looking at this, right? So 1 calorie, which is big C, so that's 1,000 calories, can raise 1,000 grams of water by 1 degree Celsius, right? That's just one way of looking at it. Therefore, these are just examples. There's nothing to memorize here. Therefore, 2 calories with a big C could raise 2,000 grams of water by 1 degree Celsius. Anyway, you can go through all this. It's just a good mental exercise to think about all the different ways you can describe how much water the calorie could raise by however many degrees Celsius. Anyway, any questions about that? All right. Like I said, there should be at least one question, a mathematical question on the study guide. And there might be one like that on the exam. Let me know if you need help, but don't let it stress you out. Here's a little chart. Obviously, this is not exact, but typical, right? It says the typical calories for a burger is 400, right? I don't know, the typical burning of calories, there's got to be something more. Yeah, in 30 minutes, yeah. I was about to say, you need more information. So they're saying, yeah, jump rope for 30 minutes and you burn 400 calories. But obviously, that depends on how vigorously you're jumping rope or how vigorously you're swimming or, how hard you're playing tennis, right? This is not set in stone. And obviously not all burgers or pizza are created equal. However, this too. This will not be on the exam. This is just an example. As usual, if you were to have anything like this on the exam, it would just be to see if you could read a graphic. So I would provide you this picture and say, about how many calories is a slice of pizza? And then you would look and say, 300. And I'd be like, hey, you're good at reading graphs. But yeah, nothing to memorize here. However, this is a really good concept for independent work if you want to look into it. Think about your favorite foods or drinks. And think about the favorite things that you like to do and write about it. Usually I like to eat this, drink that, and it's this much calories. My favorite activities to do are this, that, and the other thing, and you burn this many calories. So anyway, any questions about this? We're making pretty good time. We're not done talking about calories. And again, like I said, the calorie thing is probably the most relevant for your everyday life because you think about calories and see them every day. But as far as the semester is concerned, it's not that important. All right, now we're getting to the second main bullet point. Now it's starting to get even more important because we got done with the basic energy concepts, all the background information you need. And now that you know that stuff, we can talk about some really important stuff. ATP and cellular work. All right, the chemical energy that is released by cellular respiration is used to generate ATP. You need to know that, sure. As I said earlier in this chapter, I said that when we bring in these food molecules and they're broken down and that energy is released, remember I said the cells can't use that energy directly, and I wish we were that efficient. I said they need to be stored. That's what this is. Now we're coming back to that thing I said, but now I'm giving you a name of the molecule. It's called ATP. If anything, if I had to break down this whole chapter into one statement, and there's a lot of stuff that you should remember, but if you remember one thing from this chapter, it's that our cells use energy, or our cells use ATP as energy. I'll go ahead and break down the whole next 3 chapters for you. if anything, just remember this. Chapter 5, our cells need ATP. Let me do it this way. Our cells need ATP. How do we get ATP? Well, we burn glucose in a process called cellular respiration. That's chapter 6. That's chapter 5. That's chapter 6. Like I said, we burn glucose to do that. Where do we get the glucose? A process called photosynthesis, and that's chapter 7. So of the whole 3 chapters, if anything, you should just remember that sentence, because that's basically everything you're about to learn with a lot of details in between. Our body needs ATP. Like I said, that's chapter 5. Most important thing for chapter 5, our body needs ATP. But yeah, ATP acts like an energy shuttle. That's one way of looking at it. You could almost think of it also as a battery. Like you can imagine if your cells just ran on a bunch of rechargeable batteries. Well, your cells has a little station where you can recharge the batteries. So they bring in the dead ones, they get charged up, and then they go out to all the different little parts of the cells that need energy. That's almost like what ATP is. So again, you know that your bodies need ATP. I think the question, I'm trying to remember exactly how it's worded. Your cells directly get their energy from what? Or directly use their energy from what? My answer is ATP. ATP is how your cells get energy. Anyway, so any questions about that? All right, let's talk a little bit more about ATP. Talk about the structure of it. Again, structure and function, right? First of all, what does it stand for? Not that you need to know this, but maybe it'll help you remember what the structure is. Adenosine triphosphate, because you have this adenine base with 3 phosphates. Hence the name adenosine triphosphate. None of this should matter. You don't need to memorize this. I'm not going to ask you any questions about it. You guys aren't biochemists. You're not chemists. So, right, that's not too important. But I will say this. Even without knowing too much about chemistry, you can see that's a negative, that's a negative, that's a negative, that's a negative, right? So those things are very negative. Something I haven't told you because you don't need to know, but oxygens themselves are generally very negative atoms. Another thing I haven't told you, because you don't need to know it, is double bonds are typically very negative because there's extra pairs of electrons there, right? So these are very negative things. All that to say, these little balls of phosphates are really, really hard to push together because they're repelling each other, because they're very negative. All that to say, again, if it's harder to build a molecule, it takes a lot of energy to build it. It's going to take a lot of it, or release a lot of energy when you break it. And that's what this next slide is. Right, so there's a lot of energy to put these little 3 P's together. A lot of energy. That's called ATP, right? That's the molecule. And then once you knock one of those P's off, you release a lot of energy. And then you're left with ADP. Which makes sense, right? If you had adenosine triphosphate, because you had 3 phosphates, and then you lost one, and now you're left with 2, then you're left with ADP. And you do need to know that. You do need to know that ATP has the 3 phosphates, and ATP has the 2 phosphates. And if we're going back to this idea of ATP as batteries, you can think of ATP as a fully charged battery. And you think of ADP as that battery that's dead, or at least not fully charged, right? This one's fully charged, it's ready to go, then it releases its energy, and now it needs to be charged up again. ADP, that's the one that needs to be charged up again. ATP, that's the one that is charged. You really want to look at some, I won't say complicated, but if you want to look deep into this for independent work, if you're filling up to it, because this will be pretty deep, ask yourself, why don't we have adenosine, why don't we have this with 4 phosphates? Or do we? We're saying here, all right, this says that this is the dead one, right? This is the one that needs recharged, but there's still 2 phosphates. Why can't we just lop one of those off and have 1? And then lop another one off? What is it about ADP that says, all right, that's it? Again, that would be a pretty deep rabbit hole to go down. So if you feel like it, go ahead. But it's not important for what you need to know. Anyway, any questions about this? All right, there's some really basic stuff I'm about to teach you now. This part's gonna be really easy. This is the phosphate transfer. Long story short, before I even get into it, basically ATP loses a phosphate, and that's how we release energy, right? Everything else I'm about to tell you is just basically that in a nutshell. ATP energizes other molecules by transferring phosphate groups to them. So it's not like that P just goes off and flies into space and is gone. Technically, it's transferred to another molecule. I don't even care that you know that, though. I don't care. But it's in the book, so we're going to talk about it. So how does this do anything? Well, sometimes it helps cells change shapes. So again, phosphate group is transferred, and then a cell can change shape. I use this as an example. These are things called stomatas. These are little holes and leaves. Sometimes they need them open, sometimes they need them closed. And that's how they can do that with ATP. Just an example, you don't need to know that for the exam. Sometimes this enables transport across membranes, which at this point in the game, that sentence probably doesn't make any sense to you because we haven't talked about that yet, but we will. That's the last portion of this chapter. We're going to talk about transport across membranes. So for now, I'll just leave it at that. We'll come back to it. And that's probably the most important one. It drives the production of cells' large molecules. And again, you don't need to memorize any of this. I was just telling you why ATP is useful. We keep saying it's useful. Now your book's just telling you, giving you some examples of why. The next word for attendance for those of you online will be shape. Word I just circled, shape. Anyway, so the next few slides I'm going to show you are just some visual examples of all this stuff we're talking about here. Nothing really important, but here we go. Here we have a motor protein. So when your muscle moves, that's what this is, right? We have an ATP that transfers a phosphate group. That causes literally causes that cell to change shape, which moves the protein, which helps you flex your muscle and move your arm. And then, of course, the important thing, if anything, that you would need to know is you started with ATP, then it got used up, and you left with ATP. That's the most important thing. All this other stuff is just an example. Most important thing, again, that you need to know is you start with ATP, and then you use it up, and now you're left with an ATP, a lonesome phosphate group. Of course, we know it's not lonesome, it's actually been transferred, but you get the picture. Next slide I'm going to show you is basically the same thing. Again, your cell needs to do some work. In this case, we're transporting something across the membrane. Again, you start with that ATP, it transfers the phosphate group, which releases energy. It does its job, and then again, you're left with ATP and another phosphate. Pretty simple stuff. Same thing here. We're going to build a large molecule. We have an X, we have a Y, but what we need is an XY. That's going to require energy to put those things together. So what happens? We use ATP because that's energy, right? We use the energy from ATP, we squish those things together, and again, we're left with ADP and a phosphate. All those are examples. You don't need to know them. Again, the most important thing you need to know is that you start with ATP, that's the energized molecule, and you end with ATP. Any questions about that? All right, the next slide is going to be, the next little portion is going to be even easier because it describes what I've been telling you right here. You start with ATP, you end with ADP. That's called the ATP cycle. You're going to learn a lot of cycles for this next exam. This is the easiest one you're going to learn. It consists all of two parts. So you have ATP, you release the phosphate and the energy, and you're left with ATP, like I've been saying, right? Here's the only thing I haven't said yet, is then you can use some energy to put that P back on the ATP, and now you have ATP. Pretty simple. ATP is the energized molecule, right? You release the energy, and you have the uncharged ATP, but then you can pump more energy back into it, and then you get back to ATP. Again, like I was saying, here's a better picture of it. Like I was saying, excuse me, you could think of it as batteries, right? ATP is the fully charged battery. ATP is the not fully charged battery. It's pretty much that simple. So let me back it up to that earlier slide here that we were just looking at. Some numbers. I don't know. I want to put a question mark next to this. I'm not sure if I want you to remember that number. But there are about 10 million ATPs consumed and then recycled, right? So ATP, down to ADP, back to ATP. This happens about 10 million times each second in a working muscle cell. So one singular working muscle cell. So think about that. Think about how many working muscle cells you have in your body. Multiply that by 10 million, and that's how many ATPs your muscle cells burn every second. That's just 1 second. And also, that's just your muscle cells. Doesn't include all the other cells, brain cells, kidney cells. So yeah, I put a question mark. If you're taking notes, maybe try to remember that number, but I don't know, it's kind of trivial. So I probably won't have it on the exam, but just in case, put a question mark next to it. Next thing we're talking about are enzymes. And again, we've already hinted at this. Back when we were chapter 3, when we were talking about biological molecules, we talked about proteins, and there was that slide that showed you all the different types of proteins, like structure protein, which was the hair and the horn, and storage protein, which was a seed and an egg. I think muscle protein, I don't forget what it was called. But anyway, it showed the steak. And then one of them was called enzymes. And I told you when I first showed you that, I was like, this enzyme one, this one's going to be the most important one because we're going to talk about it later. Here we are, we're going to talk about it. But before we talk about that, there's one word you need to know, and that is metabolism. Metabolism is all the chemical reactions in an organism. That is what metabolism is. So all the chemical reactions that are happening inside of you, that's called metabolism. And as far as we're concerned, I mean, yeah, this is true. Most of them, almost all of them, require the assistance of enzymes. So without these enzymes, those chemical reactions won't happen, then you would just be dead. It's those chemical reactions that are keeping you alive. So what is an enzyme? Well, like we already learned from chapter 3, an enzyme is a protein. We already knew that. But what does it do? This is important, you need to know this. It speeds up chemical reactions. Shoot, it doesn't even just speed them up. In some cases, they just wouldn't happen at all. Like in some cases, the chemical reactions just wouldn't happen without the enzymes. But I'm going on with what your book says, which is that they speed them up. And that is true, they do speed them up. But again, keep in the back of your mind that not only do they speed them up, sometimes they make them happen where they just normally wouldn't. Another important thing is they're not consumed. So we have these chemical reactions we're talking about. We've already talked about a few of them, and we're going to talk about more throughout this section. These enzymes are not used up. You'd almost think of them like just a machine, a little cellular machine that's helping these things happen. So, for the exam, yeah, know that for sure, know that for sure, know that for sure. And this one, it's not a test question, but just so you know, again, all these different chemical reactions are happening. There's thousands of different chemical reactions, happening in you, and each one of them basically has their own enzyme. Very specific. Anyway, any questions about that slide? All right. The next concept we're going to talk about is activation energy. 2 minutes left, 2 minutes. You know what? We won't. When we come back on Wednesday, we'll start off talking about activation energy. So I guess the last word for attendance is going to be trigger. Like that trigger right there. Like that guy's holding the trigger of the crossbow. So again, you guys keep an eye on your emails. I'll put out some announcements as far as the exams are concerned. But yeah, most likely everyone's going to get to retake it.